recent years, many studies have shed light on how mobility impacts contagion processes. It is shown on different socio-technological systems as well as on various biological systems which include epidemic spreading in human population. Typically, mobility-driven epidemic processes are modeled using metapopulation approaches. However, they have limitations on the temporal aspect of the host-to-host interactions. Hence, the use of agent-based modeling as it allows researchers to determine microscopic mechanisms and movement patterns that facilitate contagion spreading. In that regard, this thesis examines how an epidemic propagates in a population of mobile swarm of agents, and determine the underlying mechanisms that result to an outbreak. We do this by employing an epidemic model on an agent-based model called the Vicsek model. The Vicsek model describes self-propelled agents that follow a simple rule: to align the direction of motion to the average direction of their neighbors with some degree of noise. This model can generate different movement patterns similar to how flock of birds migrate in unison, how school of fishes form vortices, or how bees swarm near their beehive. The collective motion of the Vicsek agents were quantified using the global order parameter, while the interactions between agents were examined by characterizing the dynamic network that they form. Meanwhile, the epidemic dynamics were investigated for the one-disease infection and two-disease co-infection. We did this for different noise levels and interaction distances, and we found out that the noise level heavily influences the collective motion but show weak influence on the epidemic spreading. On the other hand, the interaction distance affects both the collective motion and the outcome of the epidemic. If you want to know more about this, join me in my thesis defense this 17th of June. See ya!